Hello students, in the previous class we have learned about the water tanks types and what are its joints. Now what are the design considerations we'll go through it. See, we have an IS 3370 which deals with part 2, 1965, which deals with the design of the water tanks. In that the design process is limited to working stress design only, and we do have two types of the materials which we normally use in the design, in the construction, when it's concrete and the steel, and they have provided you a tabular form where the stress value for the designs you can directly adopt it from it. So the table number 21 and 22 of IS 3370 will provide you the details of the permissible stresses in direct tension and the permissible stresses in bending tension and shear stresses values for all grades of concrete, all not all grades, from M15 to M40. So the complete design of retaining wall is the working stress design. So that is why this permissible name came here. So this is wholly for the concrete, and likewise we do have for the same steel also. The table number, the next continuation table itself is for the steel. Uh, so from the same code itself. So you have the steel, the permissible stresses depends upon the thickness of your wall. If your thickness of wall is less than 225 mm, and if you are providing the steel to the face of the water, so for example, this is your wall, and this is your steel, and this is the water you're retaining. So this is this steel is called on face, and this steel is called away face. So if the steel is provided on the on face, and when you wanted to the permissible stresses for steel, that is for Fe5 250 grade of steel, it is given as 115, and if you are going for Fe41 steel, it is limited to 150. Likewise, if the thickness of your wall is more than 225, then the values are given here. So the minimum thickness recommended by S3370 itself is 200. You cannot give it thickness of wall less than 200 mm, and the minimum cover on the liquid phase is always increased by 12 mm normally. So the minimum cover is itself is 12, and plus then the minimum cover is 25, sorry, and plus 12 is 37. So let us say 40. The 40 is the cover which you need to provide for the steel if you are providing to the liquid side which you are providing, and if it is to the norm away side, then you can go for a 25 mm, no problem. So in this diagram you can see a rectangular tank and a circular tank, and if you cut this section at AA, and this section looks like this, the emphasis stands for full supply level, and this is the pressure diagram which I have clearly discussed about. And the IS 3370 also provides if the thickness, the minimum amount of steel which you need to provide, the based upon the thicknesses also. So these are the values from this. And this is all about the working stress design, which we need to discuss. But this is the main formula. Moment of resistance for an balanced section is also is given by RPD square. But before that, we need to know what is M. M is a modular ratio. This we have studied. Then K is given by M sigma CPC by M sigma CPC plus sigma ST, which is called the neutral axis factor. We have the four important factors while designing working stress design, and if you only have these values, then only we can proceed. So a small example problem, you can take any sigma C, any grade of concrete and any grade of steel, and based upon this refer IS 3370, and then you can calculate all these four values, because all these four values will give you the basic, the very important if you want to follow working stress design. This is a small example for whatever I've said here, M20 F4, and you will get the values like something like this. um, so the the circular tank is normally divided into three kinds of the uh, three kinds. So one is the flexible joint, then other we have a fixed joint. So when you have a flexible joint, you will consider the entire your circular tank as a cantilever section, and you will calculate the bending moments as per that. And you can't expect any fixed beams which are coming into it. And when you assume as a fixed joint, then you have these fixed end movements which are also affecting your steel calculations. So normally, if you go for a fixed joint, the steel calculation will be lesser, less amount of steel you will get because you have fixed movement. But extra reinforcement is provided at the joint. So what is basically what with what reference I'm talking this flexibility? This is the joint which I'm speaking about. This is the joint. So if that is flexible enough to move to anywhere, then that is called as a fixed joint. If that the joint is fixed in such a way that it can resist some movements, then that is called a fixed joint. So if you have a flexible joint, then the deflection shape itself is A B dash B. This is flexible, so the B will move to B dash. So A B dash B is the deflected shape when you have a flexible joint. But if the B joint itself is fixed, then the reflected shape of the wall will be ACB. This is the movement is resistant here. So whatever it is there, the IS 3370 always says your wall side wall we undergo a hoop tension. So hoop tension is nothing but the hoop pressure which we have already discussed in strength of materials. Whatever may be the shape of the retaining wall, and if you have a liquid inside it, and that liquid exerts some pressure onto the walls, because a fluid is a easily deformable, it never resists the forces. So it deforms, it always moves from one location to another. So it wants to get out of this retaining wall or the boundary which you are provided. Now that creates the tension in the wall, and so it wants to get out. So your walls are pulled from its ends. So for example, if you take a rectangular wall and you are storing water, this wall pushes this. So this will be in tension, and similar this wall be in tension. Similar this wall. Due to this, the joints will be in compression, so it creates a balloon kind of a thing. Best example itself is a balloon. So when you have a balloon and when you store air in it, it expands. So that is the hoop tension. Because of tension, the force itself is tension. The pressure creates a tension within the walls so that the material deforms continuously. As the balloon is rubber, it expands. Now, in the same way, your water tank will also expand. In the balloon, the expansion is in three-dimensional way. You can see in spherical. In water tanks, and whether it can be a rectangle or a circular, the deformed shape is only two-dimensional. You can have a three-dimensional thing. So that's the main thing. One is the hoop tension, which we are talking. And for the hoop tension, you can calculate still from this formula, and some design procedure is there, which we you can take any problem, you can start doing it. It's a very simple problem. Okay, thank you. We will discuss the next water tanks in next video.